All right, here we go. Unit 6, Lesson 10, Rates and Accumulation. So what we're going to be doing today is we're going to be using definite integrals, we're going to be using derivatives, but we're going to extend from the applications we've been doing with physics, right, position, velocity, acceleration, to any kind of change. So not just changing position over time, right, which is your velocity, but change in anything. So like gallons of water pouring into a pool, people lining up in a line in an hour, anything where we can measure the amount. And so if we have some function a of t, any time when we can say, okay, at this time t, there's this amount a of some quantity, if we take the derivative of that, right, it gives us the rate at which the amount is changing. And so let's think about this example here. If we have water being drained from a swimming pool, okay, and R of t represents the amount of water measured in cubic feet. Okay, so on the y-axis, we have R of t measured in cubic feet, and we have a function where t is measured in hours. And so we know that the amount of water is decreasing, right? The amount of water is going down, right? So if I take the derivative is the slope of the tangent line. Well, that slope's going to have a change in feet cubed, a change in cubic feet, divided by a change in hours. So the derivative of, right, how much water is in the pool is how fast is water leaving the pool in cubic feet per hour. The trickier one to wrap your head around is that we can do this backwards, and this is the really new critical piece of information today. If I take the definite integral, if I take the area under my rate function from a to b, it gives me the total amount of change. And so I want to back up here and I want to remind us of why this is true using examples from physics really quickly here. Right? If I take the definite integral from time a to time b of my velocity function, we know from the fundamental theorem of calculus that this is position b minus position a. Right? This is the change in position. And so the only thing that's really happening today is instead of saying position, we're saying gallons of water or people in line. Remember that this here, right, if we had the velocity graph, if we had a graph of velocity, and so say velocity looked like this, remember that this definite integral is just the area under the velocity graph. And that should make sense because if I find that area, well, I'm doing the height, which is velocity, times the width, which is time, velocity times time, that's equal to distance. And so if we had this example above where r prime of t is how fast in cubic feet per hour water is coming out of the pool, well, then we'd have the amount at time b minus the amount at time a. This tells us the change in water, the change in overall water level in cubic feet. So we'd go up from rate to amount. We're going to work through a couple examples today, starting again, we're going to do a quick one here with velocity to set the table, and then we'll keep going through some other ones. This is a very common type of problem in the AP Calc exam because you can do so many types of things with it. Okay, so real quick, right, let's just do a couple velocity examples to set the table here. Approximate the value of the definite integral from 0 to 30 of the velocity function using a midpoint Riemann sum. Great, so if we want to use a midpoint Riemann sum, let's do 3 equal subintervals. So we'll do the distance from 0 to 10, which is 10 times the midpoint value of velocity, 10 times 1.6. We'll do from 10 to 20, that's another distance of 10 times a midpoint of 3.1, and we'll do a final distance of 10 minutes times 1.6. And when you do this on the exam, you want to make sure you actually write out exactly what you're doing here. We are approximating this definite integral, so I write those little approx symbols by doing that here. And if you think about what you've got here, right, each one of these is like, okay, 10, that's 10 minutes times 1.6 feet per minute. If I multiply these things out, the minutes will cancel, and so we'll just have feet. And so whatever this answer is, and remember on the AP exam, you can stop here. You can just write this and then say all of that feet, right? It is the change in position. And how do I know it's the change in position? Well, if I think about the fundamental theorem of calculus, it's position at 30 minus position at 0. We approximate that using a Riemann sum. Likewise, and in the interest of time, I think I'll kind of just hand wave through this one. If we did the same thing for acceleration, right? Well, we don't have a table for acceleration. So we would have to use the fundamental theorem of calculus. This is the velocity at 25 minus the velocity at 5. And so we could pull those numbers up, 1.6 minus 1.6. We'd have 0, and it would be in feet per minute. And so this is the change in velocity from 0 to 25. It's the change in velocity from time 0 to 25. All right, so let's extend this. Let's extend this out to some additional types of contexts. So temperature, right? Temperature changes over time. The temperature of the water in a tub at time t is modeled by a strictly increasing twice differentiable function where W of t is measured in degrees Fahrenheit and t is measured in minutes. Okay, using the data in the table, estimate the value of V prime of 12, or W prime of 12. Okay, so I have W. So to estimate the derivative, well, we don't have, the closest we have to 12 is from 9 to 15. And the derivative, right, is the rate of change at an instant. Well, we don't have it at an instant, right? It's like they're saying, okay, estimate this derivative here, this tangent line. We'll just use these points, and hopefully it'll be good enough. And so all we'd have here is W prime of t is approximately, we would have point B and point A. And so we'd have here 67.9 minus 61.8 all over the change in time, which is 6. And I would throw the units on here. This is going to be degrees Fahrenheit per minute, right? And so this is the correct units, degrees Fahrenheit over minutes. And what this, if I were to interpret this, what I would say is this is the estimation of rate of temperature change at t equals 12. Okay, so let's look at, this is the trickier one here. Let's look at this definite integral. Use the data in the table to evaluate the definite integral from 0 to 20 of W prime of t. Well, okay, I don't have W prime of t. So this must be a fundamental theorem of calculus question. Go up one level. This is W of 20 minus W of 0. Those two things I have. 71 minus 55, and this is going to be 16. Both of these are measured in degrees Fahrenheit. So this is 16 degrees Fahrenheit. Okay, what does this represent? Now remember, if we go all the way back, right, to the most important part of today, the definite integral of a rate is an amount of change. And so if we look at this down here, we are taking the definite integral of a rate. We just found it using the fundamental theorem of calculus. And this is one that I chose this example because this should just kind of show you why this makes sense. What this is, well, I started at 55 degrees and I ended at 71. So this is 16 degrees Fahrenheit. That is the change in temperature from t equals 0 to t equals 20. And so you can imagine there might be other situations where you do have W prime of t and you have to use a Riemann sum to estimate, right? Or you have to take an antiderivative. Here, though, if you have W, you can just see the connection. Okay, one last one on this one. If we have, right, and this is where I want to show you here how these questions will often be calculator active, and I want to show you what you can do on the calculator and what you are not allowed to do. So we are going to open up Desmos here today, but I'm going to do just what you could do on a TI-84 calculator. The function W that models the water temperature has a first derivative, and so they give us this thing 0.4 times the square root of t times the cosine of 0.06t. Crazy function. Let's take a look at it. So we graph this thing. So let's say let's just call this for simplicity here, f of x, and that's going to be equal to 0.4 times the square, 0.4 times the square root of x, all of that times the cosine, I'm using x here because it just, Desmos plays nicer with it, times the cosine of 0.06 x. And so here we go. All right. This is the derivative, right? This is the derivative. And so let's see. So the temperature, yes. So this should make sense here. If we look at this, right, the temperature is increasing. The temperature is increasing. And I can check that that makes sense because my derivative is always positive, right? Now it's positive, but it is concave down. So my temperature is going up, but not as fast. My temperature is going up, but not as fast. So far, this all kind of checks out here. All right. Now let's see. Based on this model, what is the temperature of the water at time t equals 25? Oh, okay. Well, I only have up to time 20. And so here is a common structure here. Initial amount plus the derivative from b to c of whatever your rate function is will give you the amount at c, right? And assuming initial is, up to time b. And so in this case, I start at 71 degrees. I start at time 20 at 71 degrees. If I want to know the temperature at time 25, the definite integral of a rate function from 20 to 25 of, in this case, w prime of t will give me the amount at time 25, right? So you see what's happening here? Initial plus change gives me final. Now, your calculator cannot take an indefinite integral for you. It cannot take antiderivatives, but it can calculate, and if you go here and you type INT, that's the best way to do this, it can calculate definite integrals, and this is totally allowed on the AP exam. I'll show you how to do it on your TI calculator when it gets closer to, but for right now, Desmos is just nicer. From 20 to 25 of, and the nice thing here, I can just type in f of x because I already did it. Now Desmos is going to get a little snarky. It's going to say, you got to put your dx there or I'm not going to do this for you. So you put that dx there, and there we go. That is the amount of change. So the temperature goes up by 2.043 degrees to give us a total, right? If I just put in here the 71 beforehand, 71 plus the final temperature would be 73.043 degrees. Okay, that would be 73.043 degrees on this one. All right, let's see one more here. I just think it'll be useful to see one more final example here and just show you these. This one's going to be really quick because we can do a lot of this on the calculator. So a pan of biscuits this time is removed from the oven. These examples will always make sense. If it's being removed, that temperature better be going down. At time t equals 0 minutes, we're at 100 degrees Celsius. They tell us the rate at which the temperature is changing. Okay, so this is a rate function, right? This is a rate, and they give us this complicated function. So let's go ahead, let's plug this one into the calculator, right? So let's see, this is what we got here. We have 13.84 E. Hopefully it just lets me do that E to the power of, I don't want 2, I want, it's a lot harder on the iPad than it is on the keyboard, to the negative 0.173 X. There we go. Okay, so let's think about what's happening here, right? Just make sure that this makes sense. What we have here is this is how fast, okay, there should be a negative there. That makes more sense. It's how fast is the temperature decreasing. So right when we take it out of the oven, right, at time t equals 0, the biscuit is decreasing in temperature, right? And what are the units here? Celsius. What does it tell us for time here? Minutes. So when you first take it out of the oven, this is a rate function. The temperature is going down by 13.84 degrees per second. And it keeps going down, but right, the closer you get to room temperature, the slower that change keeps happening. So if we go along here, right, at 3, and I'll just do this here, f of 3 is a very convenient thing that you can do here. At f of 3, and so remember this is b prime of 3 equals negative 8.236 degrees Celsius per minute. Explain the meaning of this value in the context of the problem. I would say something like the temp of biscuits is decreasing by 8.236 degrees Celsius per minute. This is a huge trap here at t equals 3. You have to put that at t equals 3 or you haven't interpreted both parts of this question. Okay, so you get a couple points there literally for just plugging that one into your calculator. All right, sketch a graph of b prime of t. So I'm just kind of, okay, so here we go, b prime of t. It looks something like this. This one, you would just say something here like what I had said, you know, the temperature is decreasing, right, at a decreasing rate because you're getting closer to room temperature, something like that here. But the one I want to focus on is at time t equals 10, what is the temperature of the biscuits? And so this is the last one we're going to go over here today. In order to do this, what we need to do is we need to take that initial plus the derivative from a to b of the rate equals the final, right? And so if I take the initial temperature, which is 100 degrees, and I find the definite integral from 0 to 10 of this rate function, remember what the fundamental theorem of calculus tells us is this will be the temperature at 10 minus the temperature at 0, right? It doesn't actually tell us what those two numbers are, but it tells us the rate of change. So if we know the temperature at 10, well, then we can just add that change to 100 and see what happens. And so what we need to do here, remember, int, the definite integral from 0 to 10 of that f of x function It's mad at me, got to put that dx there. All right, the temperature of the biscuits has gone down by 65.8 degrees Celsius. Everything should pass the smell check or smell test. If it's the eye test, smell check, whatever. If you had some crazy answer like it's gone down by 1 billion degrees, you would know that was wrong, right? The ones on the AP Calc exam, they always make sense. So we have 100 minus that. We can just do that all at once. The magic of Desmos here. 100 minus that. Or it's already negative, so we'll do plus that. Ooh, that's a tricky one. And so we'd have 34.183 degrees, right? So it's gone down to 34 degrees Celsius. That's like 100 degrees Fahrenheit. So that makes sense. They were piping hot. Now they're hot, but you could eat them.